Hi everyone, welcome once more to this YouTube channel at Best Science Brain YouTube channel. Today we're going to have an online lecture on advanced organic chemistry. We're still working on reaction mechanism, organic reaction mechanism. Today we'll be looking at electrophilic addition reaction mechanism. So if you're seeing this video for the first time or you're seeing the channel for the very first time, you're not subscribed to the channel, please move down to the video, to the channel's name, Best Science Brain. The video is playing on your system. You locate the channel's name, Best Science Brain. Then under the channel's name or close to it, you're going to see a subscription bell or icon. Tap on that, tap on the icon only once and get subscribed to the channel. Share our video to students, mainly those in tertiary institutions, in universities, in college education, and also those in polytechnics. So this video is meant for those mainly in 200 level of high institution or in final year of their high institution, and also meant for those who are doing their postgraduate or master degree in organic related courses like pharmaceutical chemistry, organic chemistry, or natural product chemistry. So today we're going to look at this aspect of organic chemistry, this aspect of reaction mechanism. And mind you, as we have been following the channel, we have done so many reaction mechanisms. We have done the nucleophilic substitution reaction mechanism. We have done the free radical reaction mechanism. We have done the elimination reaction mechanism, the E1 and E2 mechanism. Today, we're looking at the electrophilic addition reaction mechanism. So before we go ahead, we have to first of all define what is meant by addition reaction. So we should know that addition reaction, as the name implies, is the I just lay emphasis on this. That's why I wrote in bold letter. Is the addition of an attacking reagent across the double or triple bond of an unsaturated compound to yield or give a saturated compound or a compound with high degree of saturation. So that's how we define addition reaction in organic chemistry. The addition of an attacking reagent across the double or triple bond, or you can call it the pi bond, of an unsaturated compound to give a compound that is saturated, straight compound, or a compound with high degree of saturation. You see, is the addition of an attacking reagent across the double or triple bond of an unsaturated compound to give a saturated compound or a compound with a high degree of saturation. And then to demonstrate this, we can take an example like 18. It is the molecule that is unsaturated, an alkene in chemistry. Perhaps we are adding a molecule SY through it. S could be hydrogen and Y could be chlorine. So across the double bond. So in this reaction, S will move to the first carbon as we assume, and Y will move to the second carbon. So how you can see that. So S goes to the first carbon, Y goes to the second carbon. And when you look at it, the compound is saturated. Carbon have attained its tetravalent state here. So carbon is saturated, single bond all through. So carbon is filled up. So carbon is tetravalent, or it's bonded to 4 different groups. This carbon is bonded to 1, 2, 3, and the follow carbon that making it 4. This carbon bonded to 1, 2, 3, making it 4. Now with this bond here should now be single bond. So we now have a compound that is saturated, produce the double bond broken to give us a single bond. So that's the idea of what is meant by addition reaction in organic chemistry. So having done that, so we're going to now understand what is meant by electrophilic addition reaction. Electrophilic addition reaction. We already explained the meaning of the word electrophile in our previous videos. We did video in Introduction to Organic Reaction, Introduction to Organic Reaction Mechanism 1 and 2. We explain the electronic effect like inductive effect and mesomeric effect. We also explained the meaning of the term electrophile. So electrophile in chemistry implies an electron deficient species, normally a positive particle that is deficient electron that wants to attack a place that is rich in electron. For example, a molecule can be represented using Nu linked to E. So in this representation, Nu means nucleophile and E means electrophile. Now, when this molecule undergoes heterolytic fission, heterolytic fission means this bond is broken, whereby only one of these groups will take the two electrons, because this single bond means two electrons being shared between the two of them. So if this bond is broken, and then this nucleophile goes with this electron, this particle goes with electron, then that will make this Nu become negatively charged with excess electron, and then E become positively charged because E had lost electron. It is sharing. It brought one here, remember, and this one brought one. So let's mark this one as asterisk. So this is the one from E, while the dot is the one from Nu, but Nu takes both electrons to itself, while E goes empty-handed. So this E is called electrophile, electron deficient, and then this Nu is called nucleophile. So taking you back to what we have done before, just a revision process before we go to what we have today. So electrophile and then nucleophile. For example, let me have chloromethane as a case study here. In chloromethane, you see, let's assume that in this process now, or let me not use in this process, yeah, this electron shared here is pulled away by chlorine. So that make this chlorine become negatively charged, having excess electron, while the methyl will now become positively charged, having lost electron in sharing with chlorine. So which of them now is the electrophile? Electrophile is this one that has positive charge, which is the carbocation, becomes electrophile, while this one that has excess electron becomes the nucleophile. So you have to understand the concept of the word electrophile. So in this reaction, we are talking about electrophilic addition of electrophile to compounds. So electrophilic addition reaction. We have already explained the meaning of the word addition. We're now bringing in this new term, electrophilic addition reaction. So having done that, so let us define the word electrophilic addition reaction. So electrophilic addition reaction, by definition, is a reaction which involves an initial attack by an electrophile. So any reaction whereby electrophile attack first is called an electrophilic addition reaction. So it's worthy to note that during such reaction, after electrophile has attacked the substrate or molecule, the nucleophile will still attack, but nucleophile will attack later. So in a reaction, wherever electrophile attacks a substance, nucleophile will also attack the same substance. But what we're saying here is that electrophile will attack first, then later on, nucleophile will now attack the carbocation formed by electrophile. So we should know that here, electrophile attack the molecule first to form a carbocation, then afterwards, nucleophile will now attack the carbocation. So any reaction whereby electrophile attacks the carbocation first is called the electrophilic addition reaction. But any reaction whereby the nucleophile attacks first is now called nucleophilic addition reaction. So try to differentiate the two. The nucleophilic addition reaction, this one, electrophile is the one that makes the first move, that attacks the substrate first. Well, that's why we call it electrophilic addition reaction. But if in a case whereby the nucleophile makes the move first, so we now call that one nucleophilic addition reaction. So we're going to treat nucleophilic addition in our next video. But for now, our focus is on electrophilic addition reaction, a reaction whereby the electrophile attacks the pi bond of either the alkene or alkyne first. So what it means is that this reaction is common among alkenes and alkynes. So electrophilic addition reaction is very common among the alkenes and the alkynes. So having studied that, I understood what is meant by electrophile and nucleophile. What are the common electrophiles in chemistry? So the common electrophiles we encounter include, so the common electrophiles are normally positively charged electrophiles. So halonium ions. Halonium ions means ions of halogen that contain positive charge. So this is called chloronium ion, from the word chlorine, chloronium ion, bromonium ion, and this is called iodium ion. So these ions are also electrophile because they possess positive. They are electron deficient, as you can see there. So these are electron deficient, so they are electrophiles. Another example of electrophile is also hydrogen ion. Is also another electrophile which we encounter often. Neutronium ion is also another electrophile which we encounter. You see, they are all positive. That means they are deficient in electrons. So we are going to meet these electrophiles as we go on in this topic. Now, before we go ahead, we need to understand alkenes first. We need to understand what are alkenes before we go ahead with the electrophilic addition reaction. Okay, the alkenes, otherwise called olefins. Alkenes or olefins. Okay. So what are alkenes? Alkenes or olefins are compounds that have double bond. They are unsaturated hydrocarbons. So alkenes, unlike olefins, are unsaturated hydrocarbons with the general molecular formula CnH2n and N starting from 2. That N means number of carbon atom with a double bond between adjacent carbon atoms. So that is alkenes between two adjacent carbon atoms. So that's the alkenes for us. So they are unsaturated. And then this kind of reaction we are talking about is meant mainly for alkenes and also for another class of organic compound called alkynes. Although today we're going to look at the reaction of alkenes. Our interest will be on alkenes today so that the lecture will not be so lengthy. So we're going to discuss the electrophilic, all the addition reaction of alkene normally take place by the electrophilic addition reaction. Now let's look at the structure of an alkene. Or let's take the first member. The first member will have N as 2. So if N is 2, substitute 2N with 2, have C2H2 times 2. That gives us C2H4. And this first member is called 18. If I want the second member, I'll use 3 in place of 2, C3, H2 times 3. Replacing N with 3 now, I have C3, H6 called propene, and so on. I can still build all the members by adding the CH2 group. Since it's a homologous series, add CH2 to every member. So 1 carbon plus 2 gives you 3. 2 plus 4 gives you 6 without using substitution method. 1 plus 3 gives us 4, and 2 plus 6 gives us 8. This is called butene, and so on. So I can generate the members either by substitution using numbers here, numerical values here, 2 from 2 upwards, 3, 4, 5, or adding CH2 to every successive member to generate the next members. So that is the alkene for us, giving us the idea of what we mean by alkene. Then we're now going to look at the structure of alkene. The structure of alkenes. Let's take the first member for instance. Let's take 18C2H4. So when you draw the structure 18, you should know that between the two carbon atoms, you're going to position a double bond here. That is it. So it has only two carbon atoms in each structure, and then there will be a double bond between the two carbon atoms. Then, and whenever you position a double bond, you have to abstract, remove two hydrogen atoms, either below the plane or above the plane. Choose any position, either below, and abstract, remove two hydrogen atoms. Just bear in mind that two hydrogen atoms should be removed from here. So now fill the other ends with hydrogen, H, 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 H. So that's the structure. So I can still draw it this way, whereby remove the hydrogen atoms on top of the plane and then put the double bond here and then fill this other place with this. So it's the same compound that I have drawn. So the two of them are the same thing. 18, 18, making it very simple for you to draw. So that is it. Then if I have propene, for instance, C3H6. To draw the structure of this one, there are three carbon atoms, 1, 2, 3. Having done that, then the double must be somewhere between, and it must appear only once. So either you put it here or you put it there. So then you put it here, then we'll have this. At this point, I'm going to remove carbon atom with adjacent carbon, the two, I pull out two hydrogen atoms, sorry, then fill up the other places. So we have this, have this, have this. So hydrogen, 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 hydrogen. So that's it. Can you see? 3 and then H6 propene. Should I put the double bond on this side? That means I can remove hydrogen atom either from the lower plane or from the upper plane. Then I'll fill up the other vacancies I have there. We'll have this, that, this. So two are removed. So this structure and this are the same thing, the same propene. So you have to be conversant with this, with ordinary level organic chemistry before you talk about higher organic chemistry. So having done that, we are seeing how to draw the structure of alkenes, the structure of propene, and the structure of other alkenes can also be drawn by this method. So having done that, we're now going into or to explain what is meant by we're now going to explain what is meant by symmetrical and unsymmetrical alkenes. So when do we say that an alkene is symmetrical? So an alkene is symmetrical. Let's look at an example. This example can help us explain what is meant by symmetrical alkene. This is a thin structure. An alkene is symmetrical when the sp2 hybridized carbon, that is, when I say sp2 hybridized carbon, means the carbon atoms that are closest to the double bond, the two of them, contain the same group or number of groups or atoms. Look at this carbon, it's carrying two different hydrogen. This carbon is also carrying two different hydrogen. That means it's a symmetrical alkene. So if I should divide the alkene from this plane, I will have two equal halves, with one being a mirror image of the other. So we call such alkene symmetrical alkene. So understand the concept, because we're going to be using the thing in this reaction mechanism, symmetrical and unsymmetrical alkene. Now let's look at this one also. Let's look at this alkene and see whether it's symmetrical or not. So look at this alkene. So the question is this alkene symmetrical? So the answer is yes. The alkene is also a symmetrical alkene. This alkene is called butyene. It's symmetrical alkene. Why is this symmetrical? You look at this carbon. Remember, our interest is the carbon nearest to not this other carbon at the extreme. The carbon, they call this one A. The carbon nearest to the sp2 hybridized carbon. The carbon atom bearing the double bond. That's our interest. So this is linked to only one hydrogen atom and linked to only one hydrogen atom. That makes it symmetrical. So one hydrogen here and also one hydrogen there. So that means a symmetrical alkene. Okay, assuming that we have CH3 here and also CH3 here, methyl group here. So is this alkene symmetrical alkene? Looking at it very well. So this alkene is also symmetrical alkene. Why do we say symmetrical? Because these two come out to have the same group, CH3 and also CH3. So this alkene is a symmetrical alkene. What if I replace the CH3 here with hydrogen? Would I say that this alkene is symmetrical alkene? You look at it very well before we now decide on whether it's symmetrical or not. So this carbon here is carrying the methyl group CH3. The one is carrying hydrogen. These groups are not the same, they're not equivalent. So this alkene here is unsymmetrical or asymmetrical, as you pronounce this. Unsymmetrical or asymmetrical alkene. So you see that. So what of propene? Let's look at propene structure and see whether propene is symmetrical or not. Let's look at propene. This is propene structure. Is propene symmetrical or not? Look at the double bond, and our focus is on the sp2 hybridized carbon, the carbon atoms that are close to the double bond. So if you look at them very well, so is this alkene symmetrical? The answer is no. This is unsymmetrical. This alkene is linked to only one hydrogen, while this is linked to two hydrogen atoms on equal number of hydrogens. So this is unsymmetrical alkene. So we have to understand the concept of symmetrical and unsymmetrical alkene. So having done that, we can now go over to electrophilic addition mechanism in alkenes. So and see how it goes. So we'll go look at electrophilic addition reaction mechanism. So the steps involved in electrophilic addition reaction mechanism in alkenes. So let's see how it goes. Takes place sometimes in 2 steps and sometimes in more than 2 steps, depending on the alkene or the reaction we are talking about. So the first step is the attack of the pi bond in the electrophile, forming the carbocation. So step 1 is attack of the pi bond. Pi bond means the double bond. Double bond to the electrophile, forming a carbocation. So that is it. Let's look at this. This is an alkene. So we don't need to put anything on it. Okay, let's put our group R there. That's alkyl group. An alkyl group there. And then plus, they'll have a molecule consisting of electrophile, nucleophile, and electrophile. So 2 parts of it. So for you to generate electrophile here, that means there's going to be a heterodytic fission whereby this electron moves to nucleophile. The 2 electrons go to nucleophile, while the electrophile now become positively charged. And then the pi bond moves to this. Because remember that the pi bond contains excess electron. Because when you see 2 bonds, it means 4 electrons are shared here. So the pi bond is rich in electrons. So electrophile, being electron efficient, tends to attack the pi bond so that it can become electron rich. So you now have this formed, R, carbon under R. Then the bond breaks to a single bond. We now have this. The electrophile will now attach itself here by means of this bond we use to form a bond with electrophile, which is electron deficient. We'll go to this carbon. And then since the electron shared by these 2 carbon atoms have been pulled to this carbon, that makes this carbon become somehow deficient electron. We'll now give this one positive charge. This is now called a carbocation formed. Carbocation is produced here. So that's the first step involved in this reaction called electrophilic addition reaction. Then step 2, second step involved in this reaction is that the nucleophile now attacks the carbocation to give the addition product. So attack of the carbocation by the nucleophile to give us the final product. So this is the carbocation. You bring it down here. R, C, R, then our E, electrophile already joined there. Then R, then positive plus the nucleophile that already left. Remember that the nucleophile was must have left with excess electron in the first stage will now come in because it has excess electron. Remember that this plate is positive charge and requires electron to attack this carbon here. So we now have the final product produce R, C, R, and then E, electrophile, then C, R, and then the nucleophile coming in to form a bond or to supply electron to form a bond with this. These two electrons will now make up a bond. So this is the final product. So that's how it goes. So let's go through it once more. Let's go through it once more. So in this reaction, the electrophilic addition reaction, the simplest one is the one that involves two stages. In the first stage, the pi bond of the alkene or double bonded compound is attacked by electrophile. But before then, the molecule where electrophile is found will undergo Higgs fission, whereby the electron here, remember that two electrons are shared here, is pulled away completely by the nucleophile. So why this one will now become positively charged, electron efficient? It wants to get electrons. So you're going to attack a center, or you're going to go to a center that has rich electron, that has a surplus electron, which is this pi bond. We take it to form a bond here. One of the bonds, or this bond means two electron will now be linked to this electrophile. And then if this is removed, this plate becomes electron deficient because the electron is shared with this one have been pulled out. So it becomes positive charge called cation. Then the nucleophile departs with the two electrons and becomes negatively charged. The second stage is that the carbocation, which is formed here, will now react with the nucleophile. It comes to this point. Nucleophile has excess electron. So it comes to this point to attack the carbon that has electron deficiency to give you the final product. So that's the major mechanism that occurs during electrophilic addition reaction. We're now going to take the first or the most common electrophilic addition reaction, which is addition of hydrogen halides. Addition of hydrogen halides. That's the most common electrophilic addition reaction. And see how it goes. So number one is addition of hydrogen halides. Hydrogen halides are compounds or binary compounds that contain hydrogen and halogen. You can represent them generally using the formula HS. So where that S can be chlorine. If it's chlorine, now have HCl. If it's bromine, you have HBr. If it's iodine, you now have HI. If fluorine, you have HF. So these are the hydrogen halides. So we see how we're going to look at how they add to double bond or to alkenes. So an example is, let me use 18 as an example. 18 as an example of an alkene with a simple alkene. So this is 18. So take any hydrogen halide of your own choice. Let me use HCl here. So in this addition reaction, you see that hydrogen goes to this. Before I go ahead, before I talk about it, we're going to divide this reaction into two. We're starting with symmetrical alkenes, please. Symmetrical alkenes. Then after, we'll look at unsymmetrical alkenes. So addition of hydrogen halides involving symmetrical alkenes. So this alkene is symmetrical. I explain what I mean by symmetrical alkene. Because these two carbon, each of them is carrying the same atom and the same number. This is two hydrogen atoms to this and two hydrogen atoms to this. So these symmetrical alkenes. So let's now see how the reaction proceeds. So in this addition involves, there are two groups here, hydrogen and chloro group. So one of the atoms will add a double bond to this carbon, one of them will add to the other carbon. We now have H, C, H. If I push hydrogen first, we have H here. Then if I put chlorine second, I now have Cl there. And because it's saturated, it now becomes a single bond. So this compound, if you want to name it, a number from the carbon atom that has the halogen. That is this carbon. 1, 2. This is called 1-chloroethane or ethyl chloride produced. So this is what you get when you push hydrogen first and then followed by chlorine. Now, what if we push chlorine first? Yes, let's look at the situation whereby we move chlorine first. You see, we move chlorine first. Chlorine goes, let's say, move chlorine to this carbon and move hydrogen to the second carbon and see whether the name will change. We now have this product, H, C, H, H again, H, chlorine coming here and hydrogen going there. Will the name change? Let's see. In also numbering the carbon chain, I'll also start from the carbon that has the halogen, number 1, number 2. I'll say at the same 1-chloroethane. So, or chloroethane. So that means if we are adding halogen halide to a symmetrical alkene, does not matter the order, whether you put the hydrogen first, push it first, or you push the halogen first. So you still get the same kind of a compound. So let's take another symmetrical alkene apart from using 18 to demonstrate whether this is actually true. So another symmetrical alkene I want to use is but-2-ene. But-2-ene is this. CH3. So this compound is but-2-ene. I hope you agree with me that this is but-2-ene. Yeah, it's but-2-ene. If you want to find out, open the structure from your elementary chemistry, open the structure. This is CH3 at the extreme, then C, H, H. So the same compound, but-2-ene. Look at it very well. So this is but-2-ene. So if you want to name it, you name from the end that will give the smallest value to the double bond. That's the principal, not that group you have here, about the double bond. So 1, 2, 3, 4. So 2 and 3. You start from this end also 1, 2, 3, 4. So any end worse, because you start from the end, you're going to have 2, 3 to the doubly bonded, the carbon atom that have double bond. For start from this end, you also have 2 and 3. So any end is valid. So we want to name it, take the smaller number 2, if you want to start for this side, or 2. Out of the two numbers, the smaller number goes. This is now called 2-butene or but-2-ene. So this compound and this are the same thing. How are they the same thing? If I compress this end, I'll have CH3. Compress this end, I'll have the same CH3. So you see that they are the same thing. So don't get confused when you see organic structures. So let's see now. Let's ask ourselves, is this alkene symmetrical alkene before we continue the addition process? Yes, this alkene is symmetrical. Why do I say symmetrical? If I break the double bond here and look at the carbon closest to the double bond and see the group that carry, there are two groups, 1 hydrogen and 1 methyl, 1 hydrogen and 1 methyl. Not only that there are two, there are also similar groups. So if you divide into 2, you have 2 similar halves. So that means this is a symmetrical alkene. Okay. Now let's now go ahead and add. Let me just open the structure for clarity's sake, to avoid confusion for those who are weak in organic chemistry. So if I have this, open the structure very well, and then let me add any of these. Let me choose hydrogen bromide. So the addition reaction can go in 2 ways. Let me push hydrogen first to the first carbon before the double bond, and bromine to the second carbon after the double bond. I'll now have this structure as my product, CH3. Okay. Then CH. Under here, hydrogen comes. Double bond. CH. Here, bromine goes. And then CH3. So the bond breaks to a single because that's attracted. So pushing hydrogen first and then bromine second. I have that compound. To name the compound now, I have to name from the end that is closer to the halogen. The halogen there is bromine. I have to number from the end close to the halogen. So 1, 2, 3, 1, 2. This end is shorter. This is called 2-bromobutane. So bromobutane or butyl bromide. So secondary butyl bromide. So that is it. Having done that, what if we do it in a way whereby we do the opposite or reverse the addition process, whereby we now push bromine first, and then push hydrogen later. Will the name of the compound change? Let's see. We now have HCl. CH, and then H, this time around bromine here, and then H, hydrogen, H, hydrogen, hydrogen. So that is structure difference. So is this a different compound from this one? The answer is no, they're the same. Because if you want to number the carbon chain, this bromine is closer to this end. So this is 1, 2. The other end will give us a higher number 1, 2, 3. So we prefer this end. And that will give us the same 2-bromobutane, the same compound. So what are we trying to say in essence? What we're saying that in addition of a reaction involving symmetrical alkene, does not matter the order to which the attacking reagent is added. It's either hydrogen goes first and the other one comes next, or the other way around, you still get the same compound, long as it's a symmetrical alkene. Okay? Now, having done that, let's now look at the mechanism of this reaction before we now go to that of unsymmetrical alkene. So let's look at the mechanism of the reaction, of this reaction. So let's take one. I gave 2 examples. The first one I gave was 18 with HCl. 18 with HCl gives us this compound being symmetrical. So either way, we have chloroethane or 1-chloroethane. So let's look at the reaction mechanism. So the first step, or step 1, is addition. Okay, protonation of the pi bond. That means the pi bond attacks the electrophile. The electrophile here is the proton, which is hydrogen ion. So let's see how it goes. We have our 18 molecule. Then we'll have our hydrogen chloride. So in this one, the halogen is more electronegative than hydrogen. So it pulls the 2 electron away to itself. While hydrogen now leaves as a proton and then attacks the pi bond. So, or rather, the pi bond draw the hydrogen ion. So, end of the day, we're going to have a carbocation produced. So now I have this structure. Hydrogen ion comes here, and then this bond breaks to a single bond, and this will become positive because this carbon becomes electron deficient. While the chlorine atom leaves as an anion, or what we call a nucleophile having excess electron. So this is carbocation formation is formed in the first stage. So having done that, second stage or step 2. In the step 2, the carbocation then is attacked by the nucleophile. The nucleophile, of course, you know, is the chloride ion, which is this. So you have the reaction taking place between the 2. So you have this, and then the charge there. Then this one is electron supplier because this is electron now. You're going to attack this plate that has positive charge. So you now have this structure formed at the final product. You now have this. So this one comes donate electron here to form a single bond. These 2 electrons make up the single bond. So you see that this product is the same product as in the initial case. We have obtained the final product, which is chloro or 1-chloroethane. So you can see that 1-chloroethane. So let me bring this one a little bit up for you to see what is happening here. So this one, a bit up, have this, that, and then this. This is the carbocation being attacked by the nucleophile chlorion. It now goes to fix itself here. So giving us the final product. You have that. You have this. You have this. Then chlorine comes to fix itself here. So that becomes the final product produced. So you see that, which is chloroethane. So this is how this is how electrophilic addition reaction occur in symmetrical alkenes in the presence of hydrogen halides. Now, let me use the second example that we use today. That is the one that involve um, butyene. So if I use butyene, the same kind of reaction will take place. So the first step is protonation. Protonation of the pi bond to produce a carbocation. So this is the butyene structure, which I explained before today. You can draw the full structure if you wish, or you can draw it like this. These are butyene or 2-butene. So I can use any of the compounds, the hydrogen halides there. So the proton here, this electron moves to the bromine, being majority, while the hydrogen, these are the proton. And then the word proton means hydrogen ion, positive without any charge. So it now goes to attack it's being attacked or attracted by the pi bond. The arrow is going from here to there. So we now have this structure produced CH3, CH, and then the hydrogen ion joins this bond. This bond is now is taken to make a bond with the hydrogen ion, which is electron deficient. Then we now have this, and then CH3. So see the electron will be pulled away from this carbon. This carbon becomes electropositive. So this is a carbocation. Okay. Then step 2, or second step, the carbocation will now react. Remember that we're producing also a nucleophile, bromine ion, this with excess electron. Will now react with the nucleophile, which is the bromide ion. So you can see that we have this, and then with bromide ion, reaction continues. So this one now attacks this plate, which is electron deficient, but it has excess electron to donate to form a bond. These 2 electrons can give you a bond. We now have this CH3, then this, then CH, bromine, and then CH3. Now the compound we encounter today, to name it, this bromine is closer to this carbon, this end than this other end. This is 1, 2, 3. This is 1, 2. So carbon number 1, number 2 is saturated. It's now called 2-bromobutane. So you can see how additional reaction occur when you're using a symmetrical alkene. A symmetrical alkene. Now let's look at unsymmetrical alkene. Whether we can see experience this kind of situation or this kind of additional reaction when we're using unsymmetrical alkenes. So let's take an example of an unsymmetrical alkene, like propene, for instance. Propene has this structure. This propene. So looking at the propene structure, you see that propene is unsymmetrical because the carbon atom, the bonded to the bond, the 2 carbon atoms do not carry equal number of this carrying only 1 hydrogen. The one is carrying 3. Okay, this is carrying 2 hydrogens, so that's the right structure. The one is carrying only 1 hydrogen, so it's not symmetrical. Now, if I add any of this compound, let me pick HBr to this, I'm going to get 2 products because let's see how it goes. If hydrogen goes first to attack this carbon, I'll be having this kind of structure, H, C, H, then H here, then the bond breaks, H, bromine comes next, and then H. So that gives me 2-bromopropane. So if we put hydrogen first to attack this carbon, they call this carbon carbon A, call this one carbon B. So hydrogen comes here, and bromine goes there. We have this structure. But if we revise the situation now and push bromine first to this point and hydrogen to this point, the structure will change. We're going to have this compound Br, then H, 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 H. So when you put bromine first, you see that you're going to have a different kind of structure. Bromine coming here, how you can see, look at the 2 different structures. Then we know look at the 2 structures and take their names, whether they are the same kind of structure or whether there are different kind of structures. So you look at the structure. So this one, to name it, this is 1, 2, 1, 2. Any end can go 1, 2, or 1, 2. This is called 2-bromopropane. So for this one, this is number 1. This is 1-bromopropane. The compounds are isomers. Right? They have the same molecular formula, but different structures. But they are not exactly the same. So when we carry out the addition reaction using an unsymmetrical, no longer symmetrical now, an unsymmetrical alkene, we're going to have a mixture of two. We're going to have two different products. So 2-bromo, as you can see there, and 1-bromo. But we accept only one of the products. We're going to say that one of the products is predominant over the other one. So which of the products formed is the main product, or will occur or will be formed in high percentage, with high percentage yield. So the one that will give us a high percentage yield in that reaction is the first one, 2-bromo. The main product in that reaction is 2-bromopropane. 2-bromopropane. Now, how do you know it's 2-bromopropane? We observe in what we call Markovnikov's rule. Markovnikov is a rule given by a man, a scientist. Markovnikov gave us this rule so many years back. And the rule guiding Markovnikov is a Russian chemist. So the rule was given to us in 1869 by this man called Markovnikov. So it's a rule guiding the addition of hydrogen halides or likely compounds to unsymmetrical alkenes. So according to Markovnikov, it says that in addition of hydrogen halides or compounds of this nature to unsymmetrical alkenes, the hydrogen atom of the HL, the molecule, attacks the carbon of the double bond with a greater number of hydrogen atoms. So this rule was given to us by a man called Markovnikov, or Markovnikov's rule. So Markovnikov is spelled Markovnikov. Markovnikov. That is the spelling, Markovnikov rule. So the scientist or the chemist that gave us this rule. So a man from Russia, because they had the name sounds, his Russian name. So gave us this rule that when you want to add, if you are adding to an unsymmetrical alkene, be very careful. Look at this. The one we prefer, this is the product now, and this is the wrong product. So the first one, the correct product. If you look at the double bond, the carbon atoms called double bond, which of them is carrying more hydrogen? It is this one, A. They carry more hydrogen, 2 hydrogen atoms. You can see that very well. So the hydrogen coming from this attacking reagent will now move to the carbon carrying more hydrogen. That is to A. While the bromine will go to the carbon carrying less hydrogen. This carrying only 1 hydrogen. So that is why this is the right product. That is the Markovnikov's rule. So that is observed when we are adding, when we are carrying addition reaction across the double bond of an unsaturated organic compound. That is Markovnikov's rule. So another example, using propene, then you see use under unsymmetrical alkene compound and see the product that are going to be formed. Let's look at but1-ene and see whether the compound is unsymmetrical. But1-ene, 4 carbon. You can see but1-ene. So you can have that. So this is but1-ene. Let me put the bond here. And then that is it. So deeply hard bond, how to abstract 2 hydrogen as I explained initially. So but1-ene, because if you want the number, this is where you have the functional group. So this carbon takes number 1, this number 2. So number 1 is preferred in the IUPAC convention, but1-ene or 1-butene. So is this alkene symmetrical? Or let me just change the structure. Let it not look like the previous one I used. Let me just fill this place. And then maintain the unsaturation on this side. You see the same compound. So put one in. So let's assume that we're adding hydrogen chloride to it. So this compound is unsymmetrical. So it's not symmetrical compound. Okay, let me just draw the products under here for clarity, please. So this compound is unsymmetrical because you look at the carbon atoms carrying the double bond A and B. This is carrying two hydrogen atoms. This is carrying only one hydrogen. So this addition will follow mechanical through. So whereby the hydrogen, if hydrogen goes first, I'm going to have I can compress this place. This is CH3. So drawing long structure CH3, then CH2 for this, then link to CH, which is this. If I bring hydrogen first, hydrogen will now be here. Then this bond breaks to a single bond because it's going to be saturated at the end of the day. We'll now have H, and then chlorine will now come here. So look at the structure. If I should push hydrogen first, I will have this product. Then, should I push chlorine first? What's going to happen? The structure will change. I'm going to have CH3 also there, CH2, then CH, then chlorine now comes first, then I have CH, then hydrogen now come later. So now question is this is A and this is B. Are the two compounds the same? Let's look at them very well. Are these two compounds the same kind of compounds? So to number them, the chlorine atom will have to number the carbon chain in a way whereby the carbon of the chlorine takes this number. So for this end, it will be 1, 2, 3, 4. I number them. For this end, this is only number 1. Prefer this end. This is now 1 chloro, 1 to 4 carbon, that is butane. Then this is 1, 2, 3, 4. 1, 2, 3. So 2 is preferred. 2 chloro, butane. So which of these products is preferred as the major product, and which of them is the minor or not preferred in this reaction? The product that is preferred here is this one, 2-chlorobutane. Why is it 2-chlorobutane? It's because you look at this bond, these carbon atoms. This is carrying 2 hydrogen atoms. This is carrying only 1. And then according to mechanical rule, the hydrogen atom of this will go to the carbon that bears more hydrogen. That means you should have to move to this one. That will give you this product. This is the preferred product, while this one is neglected. So that is our mechanical rule for addition. It's observed when you're adding across the double bond of an unsaturated, of unsymmetrical alkene, which I explained before, what is meant by unsymmetrical alkene at the beginning of this video. Now let's see how this reaction, the mechanism of this reaction that involve unsymmetrical alkene. The mechanism of this reaction, addition reaction of a unsymmetrical alkene. So, which takes a different dimension from the one we have studied on or about, for what we studied about symmetrical alkene. So, mechanism of addition reactions to unsymmetrical alkene. Okay, so let's see how it goes. So let's see pick propene that we used before today. We use propene, we can demonstrate what happens. So when we use propene, the propene undergoes addition reaction. So what kind of product do we expect to have? So we have look at propene. This is propene. So you can put the double bond anywhere of your own choice, your own convenience. Put it here or there. So you put it here, that means removing 2 hydrogen either up or down. Choose any end. So let me remove it from the down plane, lower plane. So these are propene produced. So now we are not talking about addition, the mechanism of this reaction. They say use any hydrogen halide. Let me use hydrogen bromide or hydrogen chloride. So then look at the reaction. So of course the first step is formation of a carbocation due to attack or protonation of the pi bond. So that's the first step in this reaction. So in this reaction now, this electron share between hydrogen and bromine is taken away by bromine because being more electronegative, while hydrogen will now come with no electron. So it's attracted by the electrons in the pi bond. So having done that, we're going to have two kind of carbocation produced here now. So let's see. The hydrogen atom here, the living or ion, the proton, electrophile, leaving this place, can either go to this carbon A or go to carbon B, and that will give us two different kinds of a carbocation. So if it goes to this carbon, we're going to have CH3, that is this CH, hydrogen coming there, and then CH. The play becomes positive charge because the electron have been pulled away by this one to form a bond with hydrogen ion. So that is this. Then, but if the hydrogen ion goes to this one, that the proton, we're going to have this carbocation CH3, okay, and then C, then H, and then C, H, H, and the hydrogen coming here now. This place now become electron, that is positive charge because the electron have been pulled to this carbon, make this one electron deficient. So having done that, you see that we have two kinds of carbocation. This is called primary or 1 degree carbocation, primary, while this one is called secondary or 2 degrees carbocation. So why do we call this one primary? Look at this. The carbon carrying the positive charge is this one, the extreme, that is C plus, that is this one. That is the carbon, this ion. Why this one can be compressed into one alkyl group, which is C2H5. So this is C2, then H4 and 5. So you can see open this one up. So you see that it's only one alkyl group that has attached the carbon carrying the positive charge. That is called primary or 1 degree carbocation. If you have two alkyl groups, this is a T group. Have two alkyl groups. One here and one is called secondary. You have three alkyl groups. Alkyl group here, alkyl group here, alkyl group is called tertiary. We explained this in our previous video before. Like this one now, why is this one called secondary? Look at the carbon carrying the positive ion. That is positive charge. That is the central carbon there. Then look at this. This is CH3, an alkyl group. Look at this end. This is also CH3 under alkyl group. So if you compress this CH3, so two alkyl groups on the carbon having the positive charge. So two alkyl group, that means this one secondary alkyl group, secondary carbocation, that is this. Why this is primary carbocation? Because it has only one alkyl group. These are attached to the carbon of the positive charge. Two alkyl group attached to the carbon carrying the positive charge is called secondary. So we now have two different kinds of propyl carbocation. Now, we know that in chemistry, as we explained in previous video, we said that 3 degree carbocation is more stable than 2 degree, and 2 degree is more stable than 1 degree carbocation. 3 degree means tertiary, 2 degree means secondary, and then 1 degree means primary. So in a situation whereby you have two competing carbocation, the most stable one is the one that will continue the reaction. Secondary carbocation is more stable than primary. So in the next step, we're going to use the more stable, that is the secondary, which is more stable than this one. So in step 2, the nucleophile, which is the bromide ion, which is released, that's the nucleophile, that goes away. The nucleophile, which is a bromide ion, then attacks the 2 degree carbocation. So that's what you're going to have. You now have CH3. Then this is the 2 degree carbocation. That is this one. You can see compressed, or you can draw it in if you wish. The same thing as what you have here. Observe it very well. Then we're now as what we have here. This is CH3. The same thing here. We now bring in the nucleophile. This electron. This is the donated to this carbon that is electron deficient. We now have CH3, CH, then CH3, and then bromine coming this point. To name the compound, this is 1, 2, or 1 to any end gives this bromine number 2. So 1, 2, this is now 2 bromo, 1, 2, 3, 2 bromo propane, which is the expected product. In this reaction, 2 bromo propane. So you see that when you have a situation of unsymmetrical alkene, you're going to have two intermediates. You're going to have two carbocations, maybe one primary and one secondary, or one secondary and one tertiary. So when you have one primary and one secondary, that choose the secondary to continue your reaction. But if you have a secondary and a tertiary, then choose the tertiary to continue your reaction. Because tertiary carbocation is more stable than secondary, and secondary is more stable than primary. So because of this, we say that the addition of alkenes to unsymmetrical, addition of halogen halides to unsymmetrical alkenes is regioselective. Regioselective in chemistry. Addition of halogen halides to unsymmetrical alkenes, we describe it as being regioselective. So what do you understand by the term regioselective? So regioselective reaction is a reaction whereby you produce two isomers. You produce two isomers, but one of them will predominate. So you produce like the reactions with propene will produce one bromopropane and two bromopropane, but two bromopropane is the predominant product. So a regioselective reaction means a reaction in which two isomeric products are produced, possibly produced, but one of them predominates, as we observe using the Markovnikov's rule. So the word regio, R-E-G-I-O, derived from Latin, means direction. So regio means direction. So reaction that involve that is unsymmetrical alkenes are regioselective reactions. So you have to understand that. So we can take another example. Apart from using propene, we can still take other unsymmetrical alkenes and still demonstrate this. We see the follow the same process without waste of time. So that is this. So we'll look for another example and see whether it's time will permit us to demonstrate another example. And then, okay, let's look at this compound called 2-methylbutene. 2-methylbutene, another example of unsymmetrical alkene. 2-methylbutene. So to draw the structure, this is 1, 2, 3, 4. Butene means 4 carbon. But butene, 2-methylbutene. So butene, that is the name, 2-methylbutene. So since it's butene, we'll try to put the double bond. Because here could be 1, 2, or 1, 2, any end. So this is 1, 2, 3, 4. So the name of the bond comes with a dual number. 2-methyl. So methyl also be on number 2. 2-methylbutene. So that is the skeleton. We'll fill it up with hydrogen, if you wish. So this is 2-methylbutene. Mind you that this end, this place will have nothing on them, because this place should be, must have abstracted 2 hydrogen for the double bond to appear here. So no 2 atoms should be removed. So this is 2-methylbutene. Maybe this reaction with perhaps with a hydrogen chloride or hydrogen iodide. Perhaps let me use hydrogen iodide this time around, since I've been using HC and HBr. So you look at this reaction, you see that this gives you CH2, CH3. You can still compress the structure in this form. Okay, yeah, there should be hydrogen here, the arrow here, CH3, because this place is saturated, CH3. Okay, C, CH3, then CH, and then that CH3. So this alkene is unsymmetrical if you look at it very well, because if you look at this carbon, if you break this place into 2, this carbon here is carrying methyl group, this one is carrying only 1 hydrogen. So they are carrying one group each, but they are different kind of group. So you see that. So this compound can still undergo unsymmetrical, obey Markovnikov's rule of addition reaction. So the first step is the protonation. That is step 1, which is protonation or production of a carbocation. So you have this, we're going to add hydrogen iodide, whereby iodine pulls the 2 electrons away, and the hydrogen ion moves to attack the pi, or is attacked by the pi bond, right? Better that way. So because this place is electron rich, so I have to look for this one that's electron deficient. So at the end of the day, we're going to have CH3. We're going to have maybe two kinds of ions produced, two carbocation produced, and see, let's see the structure of the one that is preferable here. We have CH3 and then CH3. If I should move hydrogen first, I have hydrogen here and then CH. Okay, let's this mechanism. So the mechanism, the hydrogen attack first. So hydrogen can come to this point or can go to this point. So if I do it the other way around, I have CH3, CH3, then I have a here hydrogen attacking this point. So and this place becoming positively charged. So you look at them very well. You now look at which of them is the preferred product. They look at the cations produced in this case now. The two cations produced in this situation, and then we'll consider their nature, whether they are primary or whether they are secondary. So the two cations produced, which of them is primary, 2 degree, or is there any primary carbocation? There's no primary carbocation here. I'm seeing a situation of we have 2 degree and 3 degree carbocations. So let's see why this one is 2 degree carbocation, one is 3 degree carbocation. So why is this one 2 degree? Why is this one 3 degree? So if you look at this one very well, you look at the structure of this one, let's come down here. We have the carbon carrying the positive charge. We have the methyl group CH3 on this side. You can compress the whole of this side to have an iso group. So that gives you C3, 1, 2, 3, and then H7 isopropyl group. So you can see in this, you're going to see the central carbon kind of has 2 alkyl groups linked to it. That means it's secondary or 2 degree carbocation. Then why is this one 3 degree carbocation? Let's see. The central carbon here is this. Let's see, plus having methyl group attached to it. And that methyl group by the left, and you can compress this group. We have a T group, C2H5, that is 1, 2, then 4, 5. So you can look at it. Alkyl group, another alkyl group, and alkyl, 3 alkyl groups to the central carbon. So this is 3 degree tertiary, and this is 2 degree. And as I said, or I explained initially, when you have a situation whereby you have 2 degree and 3 degree, prefer to go ahead with the 3 degree, which is more stable. Had it been that we have 1 degree and 2 degree, as we experienced in propene, we'll go ahead with 2 degree. So 3 degree is more stable. So the next step, we're going to use the 3 degree. So the next step, or step 2 of the reaction. So in step 2, we now see the nucleophile. The nucleophile then attacks the 3 degree carbocation. You see the way it goes. So all these are very simple to understand. Most students are scared of organic chemistry, but it's not a difficult thing. So let's go to with the 3 degree. We now have CH3. We have this CH3. We have that CH. We have that. So these are 3 degree carbocation. So we now have positive charge here. We're now bringing in the nucleophile, which is the iodide ion, which will now come to this point to donate its electron to form a bond. So you can see that. So you now have the final product produced. We now have CH3, then CH3, iodine comes here now, then CH2, CH2, and then CH3. So then the compound properly, the halogen should take the lower number preference. This is 1, 2, place 1, 2, 3. So prefer to number from here 1, 2, 3, 4. So this is now called 2. There's 2 groups here, methyl group and iodo group. So we now have 2 iodo, 2 methyl butane. So we'll name iodine first because African order I come before English alphabet. So 2 iodo and then the same number 2 have methyl, 2 methyl, then they don't get chain 4, 2 methyl butane. That's the final product for this reaction. So you see, that's very interesting. Having understood the Markovnikov's rule of addition, then we also have what we call anti-Markovnikov's rule. Anti-Markovnikov's rule. So we have the anti-Markovnikov's rule. So anti-Markovnikov's rule, the spelling, I think, what is V there? So anti-Markovnikov's rule. So this takes place when we have when the reaction occurs in the presence of hydrogen, not hydrogen, organic peroxide. So this occurs in the presence of organic peroxide and involves addition of only hydrogen bromide. So it only takes place when hydrogen bromide is added. I did not talk about not HCl, not hydrogen iodide. Hydrogen bromide is added in the presence of organic peroxide. We now have anti-Markovnikov's rule. So this was studied in 1933 by a chemist, American chemist called Kahask. So that man that studied this reaction, and then we'll have a different situation this time around. So, for instance, if I have a propene, which is an unsymmetrical alkene, look at propene very well. We can put the double on here. Propene is an unsymmetrical alkene, and we're adding hydrogen bromide to it. So since it's not symmetrical, that means we're likely going to have two different products, whereby we can have this. If the hydrogen goes to this first carbon, we now have H, 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 then H, and then bromine goes there. Then you have this and that. Or we can still have a situation whereby the hydrogen goes to the second carbon. In this first one, hydrogen went to carbon A, bromine went to carbon B. To provide the order, hydrogen goes to carbon B and bromine goes to carbon A. We'll have this situation. H, C, H, then bromine here, and then H, H, then you have this. So how different products? This is now 2-bromopropane. This is 1-bromopropane. Two different products produced. So now, the two are different from each other. This one follows, which of them follows Markovnikov's rule of addition? This one, the one that follows Markovnikov is observed here. Mark is observed. That Mark means Markovnikov is observed this reaction. Because Markovnikov's rules of addition, the hydrogen atom of the compound must go to the carbon or double bond that has more hydrogen. This is carrying only one, this is carrying only two. So the hydrogen will go to this carbon, carrying more hydrogen. This is Markovnikov's addition. Why this one is anti-Markovnikov's? That is, this one occurs in the presence of organic peroxide. So you have an organic peroxide here. We now have this now become the major product of the reaction. So organic peroxide is added to this reaction. Now have this. But if there's no organic peroxide, we'll have the major Markovnikov's rule. So we'll now call this one anti-Markovnikov's product, or it undergoes anti-Markovnikov's rule. We'll call that effect the peroxide effect. The reaction that gives us an anti-Markovnikov product is called the peroxide effect. So that is it. Now let's look at the mechanism of the reaction, or the peroxide effect, or anti-Markovnikov's rule. So how does this reaction take place? So it also takes place in a similar pattern like the other one, but in this case, free radicals are produced. Look at the mechanism. So the mechanism of the anti-Markovnikov's rule, or the peroxide effect. So the first step involves that the peroxide dissociates to give what called alkyl-alkoxy free radicals. So step one, the peroxide, the organic peroxide, dissociates to give what called organic free radicals, which I can call it Alkenes radicals. That's the right name. Alkenes radicals. So that's the first reaction that takes place. The peroxide dissociates to give us free radicals. The peroxide is ROOR, where these are key groups. So that is it. So in the good dissociation and forms our what's called the Alkenes free radical. So that's the first stage in this reaction mechanism. Second stage is that the Alkenes free radical will attack the hydrogen bromine to produce a bromine free radical. So step 2, Alkenes free radical attacks hydrogen bromide. Let's just say, take the halogen there, because normally this reaction takes place in the presence of hydrogen bromide now for you to have anti-Markovnikov, not HCl, no. So to give bromine free radical. So that's the way it goes. So you now have this. This is the Alkenes free radical attacking the hydrogen bromide molecule. Remember that in this bond here, this bond means 2 electrons are being shared, one from hydrogen and one from bromine. Let's just do it that way. So this electron will split equal. That is homolytic fission, whereby this will part with this electron, this one will part with this electron. So this one now move to this to make a complete compound. We now have ROH, and then we'll have bromine radical produced. You see, that is step 2 of the reaction. So it's a very simple thing. If you followed us when we did the free radical mechanism, you understand what is happening here. So the third step, the bromine radical will now attack propene to give primary radical and maybe secondary. So let's use propene as we use as example, propene as the alkene here. So step 3 now, sorry. Step 3, the bromine radical attacks propene to give 1 degree and 2 degree free radicals. Yes, 1 degree primary or secondary, and secondary free radicals. So let's see how it goes. So this is our bromine free radical. The free radical has 1 electron, please. Not that negative charge should not be there, the error. So it shouldn't have the negative charge on the free radical, please. Just an electron on it. Then propene. So we'll have that CH2. They draw propene very well. This is CH3, CH, then CH3 is propene. Good. You can still open the structure if you wish. And you know that this double bond, one of the double bond, we want to and replace it with 2 electrons. So that is 2 electrons. So the situation can come whereby electrons will part way, where this electron will now come to this, go to this one, and this one will go to this other carbon, while bromine will now attack this carbon. So when this happens, to form a bond with this carbon, with each one electron, the 2 electrons will join to form a bond. We now have CH3, CH, a bond formed with bromine. When the 2 electrons, the electron for this one and this one combine, and then you have CH2. You now have the propyl bromine free radical. You can see to the situation whereby the bromine can still attack the second carbon, which is this one. Not this other one. Now going to the second carbon. We're going to have CH3. This one, the electron free electron will not be on this one. And the electron from this, the electron that goes to this one, that will now be used to form a bond with bromine. We're going to have CH2Br. So we have two free radicals. Just like we have 2 carbocations in the other mechanism we studied that involve Markovnikov's rule, but this is anti-Markovnikov's rule. So in this process now, which of the radicals, we now classify the 2 radicals, 1 degree and 2 degree. Which of them is 1 degree? This is, can call this one, this is 1 degree free radical. Why this is 2 degree free radical? Why did I call this 1 degree? Look at the radical group. the radical, the free electron is on this carbon, and this group can be an alkyl group linked to it. So, and then in this one, the free electron is on this carbon. This is an alkyl group, and this is also an alkyl group derivative. So, two different alkyl groups on the central carbon. While this one is the one alkyl group or an alkyl group derivative on the carbon carrying the free electron. So you have to understand that very well. So 2 degree. The next step is that the 2 degree free radical, which is more stable, will now react. Will now react with react with hydrogen bromide. So step 3 or step 4, the 2 degree free radical or probably bromide free radical reacts with hydrogen bromide again. So hydrogen bromide comes in to react with the 2 degree 2 degree free radical. So let's see how it goes. So out of these two, we now prefer this one. Why is it called 2 degree? I repeat myself again. This is called 1 degree because look at this carbon. Remember that if it's a carbon our interest will be on the carbon that is kind of positive charge. But this one is a free radical. Our interest is the one on the carbon carrying that single electron. So this group can be compressed as one. So one alkyl group. If I draw it very well, so this is CH3. Or if I compress it is C2H4, C2H4Br. It's a T derivative. Then attached to the carbon, this is the carbon carrying the single electron. So this is a more like an alkyl group derivative attached to this carbon. These two are hydrogen atoms. That gives us what we call a primary or 1 degree free radical. If I look at this one, if you look at this one, the carbon kind of radical, the free electron is this one here. I have carbon, then this, then there's a CH3 on this end, and then there's hydrogen attached to it. On the other end, you have CH2Br, an alkyl group, an alkyl derivative. So two of them attached to the central carbon. Unlike this one, you have only one attached to the carbon carrying the free radical carbon. So this is primary, this is secondary. So that's the point we are making here. So we now go to step 4, which I said that the more stable one is the 2 degree free radical. Now reacts with what? With hydrogen bromide. So step 4. The step 4 is the 2 degree free radical attacks hydrogen bromide, which is the attacking reagent. So this is our 2 degree here. So we now have that CH3. That is that. I can open the structure if you wish. You can open it if you want, or you can still put in a compressed form. Plus hydrogen bromide. There's a bond between hydrogen and bromine, and that bond involves 2 electrons. If you look at this carbon has only 1 electron. It requires 1 electron to become complete in Otte state. That 1 electron is going to pull out hydrogen free radical. Hydrogen atom will now move with its electron to join it. We now have CH3, CH, H, if this bond is formed here, and then CH2Br. The bromine atom now leaves as a free radical with 1 electron, and that's the final product obtained in this reaction, which is of course by name is 1-bromopropane as the final product of the reaction. So all these things are very important for you to know. Now the question is this: anti-Markovnikov screw is observed by, as I said, by HCl and hydrogen bromide. So HCl and hydrogen bromide are the compounds that obey hydrogen bromide only is the compound. Hydrogen bromide is the compound that follows this anti-Markovnikov screw in the presence of organic peroxide. Why is it that HCl and hydrogen iodide does not addition of HCl or hydrogen iodide does not follow anti-Markovnikov screw, even if you have hydrogen peroxide there? There are certain rules for that, because For hydrogen chloride bond is stronger than hydrogen bromide bond. So that's the major reason why HCl does not follow anti-Markovnikov rule. So it has a stronger bond than that, and is not easily broken and cannot be broken by the organic peroxides. So that is why HCl does not undergo anti-Markovnikov rule even in the presence of organic peroxide. So if you're adding HCl to an unsymmetrical alkene, it will still follow Markovnikov's rule, whether there's organic peroxide there or not. Then what of hydrogen iodide? Hydrogen iodide bond is weaker than hydrogen bromide bond. But why does it not follow anti-Markovnikov's rule? Is because when the hydrogen iodide bond is broken, the iodine free radicals can easily combine. So when hydrogen iodide bond is broken, the iodine free radicals can easily combine to produce iodine molecule. So that is why these ones cannot undergo anti-Markovnikov's rule. So you see two reasons why HCl does not partake in anti-Markovnikov's rule or does not observe the peroxide effect, because HCl bond is stronger than hydrogen bromide bond, and the peroxide cannot break the HCl bond, being stronger than HBr bond. In the case of hydrogen iodide bond is weaker than hydrogen bromide bond, but even though it can be split by the organic peroxide, but when it's split, the iodine radicals easily combine to give you iodine molecule, thereby stopping the reaction. So having done that, that's the major reaction or addition reaction of alkene, which is addition of hydrogen halides. Or most other reactions of alkenes are dependent on this Markovnikov's rule of addition. That's why we have to treat this one first. Addition of hydrogen halides. Then the next reaction we to look at as time permits us is addition of what we call ozochlorination or ozobromination. So look at addition. Number 2 reaction. We look at addition of what we call hypohalous acids. Hypohalous acids. So of hypohalous acids. What kind of acids are there? The acids are the acids, this kind of HOCl, that is this, also chlorate 1 acid, and also the one we call HOBr. So this reaction also follows Markovnikov's rule of addition for unsymmetrical alkenes. So let's illustrate this reaction. Let's first of all use a tin, a symmetrical alkene for the reaction. If I use a tin, I have CH2 plus HOCl. So in this reaction, although it is symmetrical, so it has no business with Markovnikov's rule of addition, but let's try a symmetrical alkene and then try an unsymmetrical alkene in this reaction. So you look at this reaction, you see that 18, this acid contains two major groups. The two major groups are the hydroxy group and the chloro group. One bearing hydrogen and one not bearing hydrogen. So any of them can move first. Since this is symmetrical, either this one can go first or this one can go first. We're still going to have the same product. So we now have this. We have this OH and then that HCl to give us 2-chloroethanol, the compound called 2-chloroethanol. Okay, then normally the source compounds are called halohydrines. So 2-chloroethanol belongs to a class called halohydrine. So let's look at the reaction mechanism, how this one takes place. The reaction mechanism, of course, as we know, is that the first step is formation of a carbocation, as we observe in the other ones. Carbocation. So we have the 18 molecule here, and then we'll have this. There's a bond between these two, and in this bond, the chlorine atom will form the electrophile, which means that the oxygen atom here will pull the electron away, making chlorine positively charged. So is then attracted to the pi bond. So the pi bond attracts it, pulls it. So give us of course a carbocation. So now have this produce. So now have chlorine here, and then this will become positive charge. And the hydroxide ion leaves as a nucleophile with excess electron. It pulls away the electron, it shares with chlorine. So that is a carbocation production. The next step, or step 2, is that the carbocation then reacts or is attacked by the nucleophile. Remember, our nucleophile here is the hydroxide ion. So let's go up and write it. Have it up there. So we now have this product, this intermediate carbocation, then reacting or being attacked by the nucleophile. That's the next stage. The nucleophile, of course, is this hydroxide ion that has excess electron. So when it attacks, it's going to attack the plate that have electron deficiency. That is the positive charge carbon. So you now have the final product, which I obtained initially today, which is the 2-chloro ethanol, or called hydrohydrin. Hydrohydrin. So a halohydrin, sorry, a halohydrin. So that is it, or 2-chloroethanol. So the same process. If you use HOBr, it will still follow the same kind of a reaction. Give you 2-bromo Br now be here, 2-bromo ethanol produce. So having done that, the question is, what if we use an unsymmetrical alkene like propene in this reaction? Let's see how it goes. If I use propene in this reaction, what would I produce? Let me use propene, an unsymmetrical alkene, like this propene, CH3. I must not open the chain. CH2, the same propene. Then plus HOBr. This first step is, of course, generation of the carbocation. That's the first step of the reaction. That is step 1. We get a carbocation produced. So, having done that, how does it take place? Just like the same thing we explained before. There are 2 groups here, HO and Br. So the bromine group generates the now becomes the electrophile, which is called the bromonium positive ion of bromine. It's called bromonium. That is Br plus bromonium electrophile. So that is it. So the electron is then pulled away by the oxygen atom. Then this is now a positive charge. Then is attracted to the pi bond here. So you see that was going to happen. They're going to have 2 kinds of carbocations here now, because the bromine can be here or can be there. The other on the first carbon, they call this carbon A or carbon B. So if you move into the carbon A, we have CH3, CH, then Br, then CH2. This carbon now becomes positively charged because it has lost the electron to this one. Then if we move to carbon B, we have CH3, CH, and then CH2 bromine. This carbon now becomes positive charge because the electron have been moved, shifted from it to this other one to form a bond with bromine here. There's a bond here. So, and the question, we know that in this reaction, the one that will now continue the reaction is the one that is more stable. So how to classify this carbon cation? This one is 2 degree, one is 1 degree. 2 degree because if you look at, okay, no, the error, this is 1 degree, this is 2 degree. What this one called 1 degree because they look at where you have the positive charge here on this carbon. And this carbon, you can see it there, is linked to, you have C2H4Br. So you can see that linked to this. So this is to 1 degree. Only this is the positive charge on it. Only one alkyl derivative to the carbon having a positive charge. But in this one, you're seeing this is the carbon or the positive charge, this one, and this is a CH3 here, and this is CH2Br. So an alkyl group and that alkyl group to the carbon having the positive, this is secondary 2 degree. So this one is more stable, and this one will continue the reaction. So we'll take this one as the more stable carbocation. So we'll now go to step 2 of the reaction. In step 2, the nucleophile then attacks the 2 degree carbocation. Okay. So as we say, the nucleophile then attacks the 2 degree or more stable carbocation. So this, which is CH3, CH positive, then CH2Br. When I adding the nucleophile to it, the nucleophile, of course, is the hydroxide ion, which is living, the living group, or the anion here, the nucleophile. So now I have it coming back to attack this. And of course, you're going to attack the place that is electron deficient, this carbon, and then we'll have the final product produce CH3, CHOH, then CH2Br. So that's the final product produced, which of course we can call this one 3-bromo 1,2. This is the hydroxy group, the functional group 1, 2, 3. So 3-bromo propan 2-or as a final product. So that is what we expect to happen there as a final product for this reaction. So having done that, we're now going to more reaction now, and then 1 or 2 more reactions before we end up this first phase of the reaction to continue on that phase in the next class. But the reaction of alkenes are plenty, so we can finish them in one video. So the next reaction is addition of H2SO4, addition of the 6 acid. So that's the third reaction. The third is addition of H2SO4. So concentrated or moderately concentrated 6 acid is added to alkene in a similar way by which you add hydrogen halides, and it also involves Markovnikov's rule of addition. So it involves also Markovnikov's rules of addition. So addition of H2SO4 also involves, for example, if you use a tin, this is a tin. We're adding H2SO4 to it. So let's just try to break this molecule like this, H and then HSO4 in this form. So let's separate hydrogen from the hydrogen sulfate ion and then move the respective groups. So hydrogen can go first because this is symmetrical. So this symmetrical, any of them can go first. Either hydrogen can go first or the hydrogen sulfate ion can go first to give us a compound of similar of this nature, C2 or CH3, CH2HSO4 or C2H5. If you compress this, 2 carbon, 5 hydrogen, and then 6 ethyl hydrogen sulfate. So that's the kind of product we should expect in this reaction. Then the question is this: how does this reaction, the mechanism of this reaction, will also involve the same electrophilic addition reaction, just like that of the halides. And we're going to observe mechanical screw if the alkene here is unsymmetrical, but this is a symmetrical alkene anyway. So let's see how this one goes. So the first step is protonation of the pi bond to produce a carbocation. So that's the first thing that happens here. So you have 18. So protonation means addition of hydrogen ion. You should have that in mind. So from that acid, so you have hydrogen ion coming from the acid to add on to this. So you have that. So you have this coming to this point, attacking the pi bond, or the pi bond attacking its right brother. Because the pi bond is electron rich, pulling this. So you'll see this symmetrical. The hydrogen ion can either go to this point or to the other point. So now have any of them is okay. So anywhere it attacks is okay. So give us an ethyl carbocation produced. The next step is that the carbocation is then attacked by the hydrogen sulfate ion. Hydrogen sulfate ion, which is, remember that this the acid will broke it into two parts, H and HSO4. So in the production of the electrophile, this pulls away the electron, leaving you know hydrogen sulfate, which is the electrophile, and the hydrogen sulfate, which is now the nucleophile with excess electron. So the second step, or step 2, the nucleophile, which is the hydrogen sulfate, attacks the carbocation. So you can have that. We have this. The carbocation produced is primary. So you can rearrange itself because this is a symmetrical alkene. Had it been that this alkene is not symmetrical, we'll talk about whether the carbocation is secondary. We can have two kinds of carbocation, secondary and the primary, or secondary and tertiary. We'll use the table 1 to continue the reaction. So we now have hydrogen sulfate that has excess electron to donate to the electron deficient carbon. We now have a final product, H, 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 and then H, H, and then hydrogen sulfate attaching itself here. So that's the final product of the reaction. You can see that they're very easy to understand and to also do. Then we look at if we use someone may ask a question, say, what if we use an unsymmetrical alkene like propene? Yes. If we use like propene, let's try and see what happens. So unsymmetrical alkene, the first step is also the same, protonation of the pi bond. So let me use use propene now. An unsymmetrical alkene, CH3, then CH2. No, there shouldn't be any. There CH2 should be here. This is propene. You can open the structure and see this propene observed. Then protonation of this. So this one comes into attack. So it can either attack carbon A or carbon B, because this compound is not symmetrical. This is carrying only one hydrogen, this is carrying 2 hydrogen. So we're going to have 2 kinds of carbocation produced. I'm going to continue with only one, the one that is more stable. So if the hydrogen atom comes here, so let's look at the attack. So we now have CH3, CH, hydrogen coming there, and then CH2, positive charge here. Because this carbon is losing now, becomes positively charged. Then, or if the hydrogen atom goes there, we have CH3, CH2, and then CH2, positive charge. Okay, no, there's an error here. So if the first one, hydrogen atom went to this carbon, that's okay. Second one, hydrogen atom now go to carbon, second carbon, so here should be positive. Basically becomes 3. So which of the carbocation is more stable? You have to look at it very well before we provide the answer. Which one is 1 degree? Which one is 2 degrees? This one is 1 degree because you can see the positive charge here, and this place is compressed into one alkyl group only. This is hydrogen. But the positive charge is here. This is methyl group. This is another alkyl group, methyl group. This is 2 degree. So this is more stable. So in second step, the 2 degree carbocation is attacked by the nucleophile. The nucleophile is the main part of the acid. So that is the hydrogen sulfate ion now, as we said. So that is the 2 degree. So being attacked by the hydrogen sulfate, which has excess electron, the nucleophile. You're going to attack the central carbon that has deficiency in electron. So we now have this CH3, CH, HSO4, and then CH3 as the final product. So we have to be very careful of how to get our product. The orientation of the product we're going to get matters. So we'll look at addition of water. Addition of water, which is called hydration reaction. Addition of water, which is called hydration reaction. So high is water added to alkene. So water reacts with alkene in the presence of any strong acid catalyst, usually in the presence of H2SO4. So let's look at hydration reaction and the addition, important addition reaction of alkenes. So number 4 is hydration or addition of water. Hydration reaction. So we want to first of all take an example. We're going to use a symmetrical alkene to do that. Then next we use another symmetrical alkene to do that. This reaction also follows the mechanical rule of addition. So if I use a symmetrical alkene, for example, 18 is symmetrical. So the first step, as you know, is generation of a carbocation. That is the first step. Hydration here. The first step of this reaction, or step 1, is protonation. Proton from water will attack or will be attacked by a pi bond to form a carbocation. So now I have plus hydrogen ion here. So that gives us acid catalysis required. They will now have H, H, H. Then you see the proton. Because this alkene is symmetrical, so the hydrogen ion can attack any of the carbon. You see the same product, whether it goes here or goes there, no problem. The simply become positive because this one pulls the electron. In this case, this is the carbocation produced. So this is our carbocation. So the next step, or step 2, the carbocation is attacked by the nucleophile. The nucleophile in this case. How is the nucleophile generated? Water can be presented as HOH. This is water molecule. How we got this? So in this reaction, the hydroxide ion, also a bit more negative, pulls the electron away. Give us hydrogen ion, which we use here as a proton, and then hydroxide, which is the nucleophile, which we're going to use in this second stage. So in the second stage, the carbocation then reacts with the nucleophile, or is attacked by the nucleophile. We have plus OH. So which will now attack the carbon here. So that will give you the final product, which is this, nothing but ethanol produced as a final product produced here. So you can see the product produced, ethanol. That's the major product, or the product obtained in this reaction. So you can see the hydration reaction taking place. Although you can still visualize it this way, instead of a hydroxide ion attacking this, you can still visualize this concept in this form, whereby the nucleophile is not hydroxide ion, rather is also water molecule. Remember that water has a lone pair of electrons. So that is it. You got water has 2 lone pairs of electron and oxygen. So this is the same water. So here we're taking the nucleophile not as hydroxide now, but as water. So the reaction can be perceived in this form, whereby water then attacks the carbocation produced here. So whereby you know that this place is lacking in oxygen. So what oxygen atom here, lacking an electron, sorry, oxygen atom now provide an electron pair to form a bond here. We now protonate the carbocation to form a protonated alcohol. We now produce H, 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 H. Then a bond, oxygen comes in, and then H, H, electron, a lone pair remain. One of them have used to form a bond here. And this oxygen is giving positive charge because the oxygen is somehow electrophilic, having this electron to this carbon. Then the next step is now we're going to have what we call proton abstraction. Proton abstraction, whereby the electron here, the electron returns back to oxygen and the hydrogen ion leaves or departs as a proton, or proton abstraction will take place there. So, having done that, and how is the proton abstracted? We need also water to abstract this proton, and that water molecule comes in again to take the proton away. So, and while the electron here to return back to this oxygen to make it completely filled, to have a complete filled outermost shell. So we now have H, C, H, H, then H, H, and then of course OH. And then we'll now have a hydrozonium ion produced. So you can see that. So that is the way it goes normally, not the actual way it goes. So then repeat the process. I explain the process again. In the first step, the proton attach the symmetrical alkene, any of the carbon, it can go there to form a carbocation. Then the second step, the carbocation produced is attacked by a nucleophile. This time I'm using water molecule instead of using hydroxyl. Water molecule is better used for illustration. The water molecule, on the oxygen atom, there are two lone pairs of electrons, and this place is electron efficient. So this electron is donated here to form a bond. That's the bond. And that electron will move away. That is the bond. That remains now a pair. And because the water appears to lose the electron, it becomes positive charge. But also appears to have lost electron to this carbon, or shared electron with this carbon, become positive charge. Then the electron from this hydrogen, any of them, returns back to oxygen. The water molecule comes back again to pull away hydrogen ion with that electron. The electron is given to oxygen. So this hydrogen ion goes to water to form hydrogen ion. They are now left with an alcohol produced. So I use the last example for today. The last example I'm going to use, I will use an unsymmetrical alkene. Okay, I'm going to use a compound called 3,3-dimethyl-butyl-1-ene. 3,3-dimethyl-butyl-1-ene for this illustration. So I'll draw the structure first. 3,3-dimethyl-butyl-1-ene. So butyl-1-ene is 4 carbon. You can number them 1, 2, 3, 4. Butyl-1 means the bond comes here. 3, that is methyl is here, and that methyl is there. 3,3-dimethyl. So I'm filling up with hydrogen. So there's vacancy here because of the double bond. So this is a compound called 3,3-dimethyl-butyl-1-ene. 3, let's bring the structure lower for us to see very clearly. So 3, I repeat the process. You draw 4 carbon atoms. For but, that is 4. 1-ene, double bond comes here, 1, 2. So this is but-1-ene. Then methyl group here, 3, that's the methyl group. 2 of them are on number 3. They fill up with hydrogen. And bear in mind the fact that these places have double bond. There must, have to move 2 hydrogen atoms. So this is the compound called 3,3-dimethyl-butyl-1-ene. So we're going to hydrate this compound and see how it goes. So I'm going to compress it. I will have CH2, CH, CH3. I can compress it if I wish, or I leave it open. And then CH3. That the compound will have there, the same compound, written in a different form, so you can check it very well. So we'll now talk about the first step, which involves protonation. We are talking about hydration again, but we're using a different compound. Protonation, we're going to add hydrogen ion to this. But if you look at this compound is an unsymmetrical alkene. Look at it very well. Check the double bond. So this carbon is carrying two hydrogen. The one is carrying one hydrogen. So is unsymmetrical. That means the hydrogen ion can either attack this carbon or this other carbon. So give us two different kinds of nucleophiles. So let's see. For the first one, I have CH. If hydrogen ion goes first, CH3, the bond breaks. The positive ion is now located here. Then CH3, then CH3, and then CH3. So this is called 1 degree. No, not 1 degree. We need to clarify it. We're going to find out what it is. So we're going to look at the other one. The other ion goes to this one. We now have CH2. And then also we have a CH2. This place now becomes positive because this place is now losing electron. Then CH3, CH3, and then CH3. So we look at it very well. When I look at the two of them, which of them is 1 degree, which of them is 2 degree carbocation. Look at this very well. This is 1 degree primary. It's 1 degree carbocation because you look at this group. This is where I have the positive ion, and this one is just this is just like 1, 2, 3, 4, 1, 2, 3, 4, 5, and then 6, 9, 11. This is just like you're drawing this. C5H11. One alkyl group attached to the carbon of the positive charge. These ones are not alkyl. This is primary. So we're not using this one to continue the journey. Then look at this one. The second one appears to be a more stable carbocation. Then if you look at it, this one is 2 degree. Why is it 2 degree? Look at the carbon. H, one carrying positive charge. This one, they have CH3 on this side. On the other side, I have 1, 2, 3, 4, C4H9. C4H9 on the other side. So 2 alkyl group to the carbon. Central carbon carrying the positive charge. Before we continue on this, we have to look at it very well and see whether we are going to rearrange, because we don't call 1-2 shift in chemistry. We talked about Brownian reaction in the previous video. Whether this one can be rearranged to give us a secondary, a tertiary, that is a greater stability, a tertiary alkyl group. Let's see whether this can be rearranged. Let's look at it very well. Then look at the structure once more, and if it cannot be rearranged, we continue with it. But it can be rearranged to give us a 3 degree alkyl halide. A 3 degree carbocation, which is more stable than secondary. We'll now continue with that 3 degree. So we'll now do 1-2 shift. We look at the adjacent groups is methyl group. So we can shift this methyl group here. So we shift it. We'll now have CH3, CH3, and then CH3. Positive charge now come to this point, and then CH3. We have produced a different kind of carbocation, whereby we shifted the methyl group to this point. We will now produce what called 1-2 shift, shifting methyl group from one position to another, the next position, and then changing the charge position. So you can see that this is 2 degree, yes, but this one is 3 degree. Look at it very well. Look at this carbon here. This is 3 degree. The carbon here is having positive charge. Then here is CH3. As you can see, here is CH3, and then you have another CH3 at the extreme, and then you can compress this side 1, 2, 3, 1, 2, 3. That gives us C3, 1, 2, 3, H7. So you can see you have 3 alkyl groups on this carbon carrying the positive. That means it's very stable. So the next step will now involve rearrangement. There should be a rearrangement that has happened here. The next step is that this tertiary will now continue the journey because it's more stable than secondary. So in a situation that you're going to have a rearrangement, you have to do that first. But if there's no rearrangement, you continue the reaction with the secondary carbocation. So the next step is we now have step 2, or this is step 2. The arrangement is step 2, the rearrangement. of the carbocation is the step 2. Then step 3 is the tertiary or 3rd-degree carbocation is then attacked by what? The nucleophile. And nucleophile, remember, is water. So we're talking about hydration reaction here. So don't lose focus. So we'll take the 3rd-degree carbocation, which is this, produce CH3, C, H3 here, H, then C, H3, then attacked by the nucleophile, which is water. And water, you know, has 2 lone pairs of electron on oxygen atom, on the oxygen atom or the central oxygen atom. So the oxygen will donate its lone pair to this carbon to form a bond there. So we're now going to have a protonated alcohol. So let's draw it down. CH3, C, CH3, then H, C, CH3, then CH3, and then the one of the electron you use to form a bond, OH2, and then you can open the structure of the hydrogen atoms if you wish. That'll make it better or look better. Let's put this one here, and then this one here, making it, this must become positive because the electron have been departed from it, or the electron is being shared with carbon. So that is it. Protonated alcohol. The next step is now we're going to remove one of the hydrogen atom by using also the same water molecule coming again to take away one hydrogen ion. So this is our water coming back again to remove one hydrogen ion from this, while the electron here returns back to oxygen. So you have that, the same principle, observe. So the final product now becomes CH3, C, CH3, then H, then you remove the oxygen now becomes complete with 2 lone pairs. That gives you your normal hydroxide group, OH. Why we have CH3 here? And then this one takes this hydrogen ion. Taking a hydrogen ion means hydrogen ion goes out without electron. The electron it has come back to oxygen. So you find electron-rich center here to give you our hydrozonium ion within this form, positively charged, or you can write it this form, H3O, positively charged. So having done that, we have not exhausted the reactions of alkenes, but we have done a great part of it today, the lecture. There are other reactions that involve halogenation, there are few remain anyway, halogenation reaction and other reactions of alkenes, like reaction with alkenes, and then the one we call the oxidation and the degradation reactions. But they all follow similar principles of addition reaction. Perhaps we may still do some other ones. Let's say if the time permits us, we can still do that of a halogenation reaction of alkenes. Let's see how it goes. Let's do that one before we quickly round up. So, halogenation of alkenes. Now, add the halogens to alkenes. How does it go? So, let me use a symmetrical alkene. For example, let me use 18, which is symmetrical alkene. Halogenation. Well, the first step, of course, is production of a carbocation. So that's the first step, carbocation production. So how does it happen? The halogen, like chlorine, now consists of 2 atoms. So, and you know that in chlorine atom molecule, halogen has 7 valence electrons around it. So there should be 2, 4, 6. 2, 4, and then 6. One electron was from here, was used to form a bond here, and one electron came from this one also. So there's going to be a fission process to give us a carbocation, to give us an electrophile, please. One of the chlorine atoms goes with the 2 electrons. One becomes electron deficient to give what we call chloronium ion, a kind of halonium ion, a positive charge ion of which should be written as HCl plus when electron departs. So this electrophile will now attack or is attacked by the electron-rich pi bond. So when this happens, we're going to produce a carbocation that is specially shaped. So the carbocation has this structure of this, produce the chlorine atom comes or the halogen comes there, while the hydrogen atoms will be seen in this form. So you see that chlorine brings one of its electron to form a bond. This one of the electron here used to form a bond here, while one of the pi bond used to form the other bond. So chlorine is now left with using one is now left with two electrons. Since you use only one to form a bond here, now left with two lone pairs here. So chlorine is deficient now. We will now give chlorine positive charge. So we have this is the carbocation produced, and then we now form electrophile. The electrophile form is this chlorine ion, the chloride ion. This is now rich in electron because it has pulled away the electron. Is share with its fellow chlorine. This is the chloride ion electrophile. So you see the first step that takes place during halogenation reaction. Then the second stage is that the nucleophile will now attack the carbocation in the backside attack. So step two is nucleophile. The nucleophile, of course, is the chloride ion attacks the carbocation, or what would I call it? I'll call it the coronium ion, because the positive charge is on the chlorine. So it's production of this is production of halonium ion. That is the first step, halonium ion production, not carbocation. Because the positive ion resides on the halogen, not on the carbon. So the nucleophile attacks the coronium ion. So you can see that. So we're going to have it in the backside manner. So that is the way it goes. So you have the structure. You draw it again. You draw the structure once again. And then you have this. And then you complete it. You have that positive charge. And then the nucleophile, which is this, attached on the back on any of these two carbons. So let's find it here. So nucleophile attached from the back, and then you have the final product formed. Our final product will now become give us this structure CH separating chlorine now comes here to join itself with a bond, while the chlorine goes to the other carbon. Chlorine, then H and also H, giving you 1,2-dichloroethane as our product. So the next reaction is addition of halogen and water, or halogen water. So addition of halogen and water is also another reaction of alkene. Then we also have addition of carbenes. When alkenes react with halogen in presence of water, they form compounds we call halohydranes, 1,2-halohydranes. So the reaction is also involves similar step as we have on the board. So we also have addition of carbenes. We also have Aussie halogenation reaction. So let's look at addition of carbenes quickly. Addition of carbenes. With that, I think we have done justice to the topic. So addition of carbenes. So when we did reaction intermediates, we also encountered carbenes. This video in our tutorial, or in our YouTube tutorial, we did the reaction intermediate. We mentioned carbenes. Say carbenes are highly reactive reaction intermediates. So carbenes are highly reactive reaction intermediates. We call them carbenes. So carbenes are highly reactive reaction intermediates. An example of carbene is the methylene. The simplest kind is the methylene carbene. So methylene is the simplest carbene. We call it methylene CH2. Now the methylene carbene, and methylene exists in two forms. We have the singlet methylene. We also have the one we call the triplet methylene. So singlet, methylene, and triplet. What is the difference between the two? If you draw the structure of the carbene, they are the p lobes or p orbitals of carbene. So the singlet carbene, carbon here is sp3 hybridized in singlet carbene. So we have the structure on the board. This is the singlet carbene. And the singlet carbene, the two electrons are in one p orbital. That we'll call the singlet carbene. Then, while the other p orbitals are empty. So, then we have the triplet carbene. In triplet carbene, what is the difference between the two? So, this is the triplet carbene. In this one, the two electrons are separated, one in each p orbital. So in the triplet carbene, carbon is sp hybridized, not sp3 hybridized. So this is called the triplet carbene. So it's different from the singlet carbene. And then you see the difference between the two kinds of carbene. But in organic chemistry, we have our interest is mainly in the singlet carbene. That's where we have our interest. So let's see how carbenes react with alkenes. The reaction of alkenes with carbenes in chemistry say is stereospecific sign. Stereospecific sign. So reaction is that is what do I mean by a reaction being stereospecific sign? Means that the reaction gives a kind of product whereby the substance are on one side, like either giving you cis product or giving you trans product. That's what it means by stereospecific sign products or reaction. For example, let's look at this alkene. We have this is an alkene. So we can draw any alkene can be used here. We have this could be a group, either hydrogen or any other group. Let's just spread the atoms. So this kind of position or spatial distribution is cis, because a cis compound has similar groups on the same side. You can see R and R group on the upper plane, H and H group on the lower plane. We call this kind of compound cis product or cis isomer, cis compound. So if we're adding a singlet carbene to it, how will the reaction go? And singlet carbene normally has 6 electrons in the carbon. So we have that. So we're going to have a product of this nature whereby this bond breaks. This carbene brings 2 electrons to form a bond here. This bond, this bond came from these 2 electrons of carbene, and then this is the carbon atom of carbene with its 2 electrons. And then the other electron here is from the pi bond. So this bond is the 2 electrons from carbene. Then this bond here is the one of the pi bond electrons. So you have that. You have R here, and have H, R here, and then H. So you see the product formed. We can see represent the product in this form, in a proper form. In this way, you have this. So that is the more like a cyclopropane chain, and they have R here, R there, H here, and also H there. So that the products formed. So that the same thing. So we'll have forming a cis product. Cis because the R group are on the same side and the H group are on the other side. So this confirms to this. This is a cis reactant and gave us a cis product. That was why we say that is a stereospecific sign reaction. So you can see that. So they will now have a cis dialkyl compound. Then if we have a trans compound, trans, what we mean by trans? The word trans means across, whereby the R group are on different sides across, and the H groups are across each other. We call this one trans reactant. And then with a carbene, okay, we see form a kind of product whereby in this situation now, we now have this kind of product, but this time around, the R and the groups are not on one side. You have one R here and then H. You have then what here now? H and then you have R. You see, a different kind of product. So you see that this is trans. The R groups and then different groups on one side. That means of trans. Cis, similar groups are on one plane. R, H down as you have in the reactant. But look at the reactant here. It's different groups up and different groups down. Trans. Likewise, the product form here. Then also, this will also give us also another compound that looks like this, like the brother or a mirror image of it. Which of that one we now have a situation of this, whereby it appears that this side is changed position with this side. You have HR, and then you have this side ROH. So this is more like a mirror image. This is a mirror image of this one. They change their position or their respective position. So when we have this kind of situation whereby you have enantiomers or compound that are mirror image of each other produce in equal amount, we call that a racemic mixture. A racemic mixture. A racemic mixture. But in this one, in the first one, whereby we have this one, and there's no how we can get a different one. This is cis gives rise to a cis compound. We call this one a meso compound because this one has no mirror image produced, a meso compound. But the trans gives us a racemic mixture. So that one will say that the reaction is stereospecific, whereby the reactant will assume the product will assume the same form as the reactant. You have a cis reactant, you also have a cis product. Groups are up. The product, they're also up in the product. H are down on the lower plane, product, they're also in the lower plane. But if the reactant is a trans compound, whereby the groups are on a plane on different groups on the upper plane and different groups on the lower plane, then the products will also give you the same kind of product but we're going to have a racemization taking place, whereby you have two compounds which are mirror images to each other. So with that, we have come to the end of this tutorial or this our online lecture on electrophilic addition reaction, which I told you normally involve the alkenes and the alkynes, compound that have double bond and triple bond. We have done justice to compound that have double bond. We have done enough work on it. There are many few of them which involve the Aussie mercuration and demmercuration, and then the other one, so which you can read up on your own. So for the same process, you can still get the idea. So we're going to, next time, we will look at the second part of this video that involve the alkynes, a reaction that involve alkynes. So electrophilic addition reaction involving alkynes. We did alkenes today. Then finally, we'll see look at another one that involve a nucleophilic addition reaction. That one will involve the carbonyl compounds. So always stay connected to this video or to this channel. Subscribe to the channel. If you are not subscribed, share the video to students in higher institutions that are offering science courses, organic chemistry precisely, or people who are in biological and physical science or engineering first, second year students, and also those in doing their postgraduate studies in chemistry, organic chemistry precisely, that they'll find the video interesting. So thank you very much for staying connected, for listening to us, for having your time to listen to us. Stay connected, like our video, share our video. Thank you very much.